Hi everyone, welcome back. So if you joined us for our recent explainer on regression metrics, you know exactly how absolutely crucial it is to figure out if your model is actually doing its job. Well, today we're tackling the classification side of that exact same question. I've brought along our robotic assistant, Techie, to help us out. We are going way beyond the basics today to look at precision, recall, and the F1 score. We're going to see exactly why relying on accuracy alone can genuinely mislead you and how to choose the right tools to measure your success. All right, let's jump right into section one, the three metrics, and what we'll call the accuracy trap. So let's start with the metric everyone intuitively reaches for first, accuracy. It's incredibly simple, right? It's just the percentage of predictions your model got right overall. Out of 100 guesses, how many were correct? In a perfect world, it's actually a great metric. But in the real world of machine learning, it becomes genuinely misleading. This happens in one very specific, very common situation, when you're dealing with rare, uncommon events. Think about detecting a rare disease in a massive population, or spotting a single fraudulent transaction among millions of legitimate credit card swipes. In those scenarios, relying on this simple percentage can completely blindside you. To put that into perspective, imagine you have a dataset where a rare disease only occurs in 1 out of every 100 patients. You build a model, and it literally just guesses no every single time. It never diagnoses the disease once. Well, guess what? That model is 99% accurate. It scored incredibly high purely because the rare event is, rare. But think about the actual value there. It's zero. It has absolutely zero value because it never actually catches the thing it was built to catch. This is exactly why accuracy alone isn't enough. We need better metrics that don't get fooled by rare events. So let's move to a better tool. Precision. Precision asks a much narrower, much more specific question. Of everything the model flagged as positive, how many actually were real? Think of precision as the model being very strict and cautious. A model with high precision rarely raises a false alarm. It absolutely hates being wrong when it cries wolf. So when a high-precision model says yes, you can be highly confident that it is genuinely right. It's exactly the metric you want when a false alarm is highly disruptive or super expensive. And then, on the other side of the coin, we have recall. Recall asks a different question entirely. Of everything that was actually positive in reality, exactly how many did the model manage to catch? Think of recall as loose and catch-all. A model with high recall is basically paranoid about missing something. It rarely misses a real case because it flags absolutely anything remotely suspicious. It catches almost everything that's actually there, even if it ends up flagging some innocent things along the way that turn out to be completely nothing. So, the crucial point here is that these two naturally trade off against each other. It's like a giant seesaw. You can't usually have perfect precision and perfect recall. If you make a model stricter, meaning it only flags things it's incredibly confident about, your precision goes up because you avoid false alarms. But your recall goes down because you inevitably miss some subtle, real cases. Conversely, if you make it looser and willing to flag anything suspicious, your recall shoots up because you catch everything, but your precision plummets as you just drown in false alarms. It's a fundamental balancing act. So how do we evaluate a model without constantly looking at two shifting numbers? Well, that's where the F1 score comes in. The F1 score specifically balances precision and recall together into one single metric by calculating the harmonic mean of the two. What that effectively means is that a model literally cannot hide terrible performance in one area behind great performance in the other. If a model has 100% recall but 1% precision, the F1 score will heavily penalize it. It forces the model to be reasonably good at both, giving you a much truer picture of its overall health. Okay, moving on to section 2. Let's make this trade-off concrete with a real example. Medical scans versus spam. Imagine we're building an AI to detect a serious medical condition from an MRI scan. We have two models to choose from. Model A is our high recall model. It's built to catch nearly every single real case, but that means it flags some healthy patients for a closer look that turns out to be totally unnecessary. Then we have Model B, our high precision model. This one is cautious. It only flags a scan when it is genuinely 100% confident, which means when it raises a flag, it's very likely real, but some genuine subtle cases slip through without being flagged at all. So which one do you choose? Well, for a serious medical condition, the cost of a false negative, missing a real disease and sending a sick patient home, is devastating. It is far more costly than a false positive, which honestly just results in an extra follow-up test to confirm they're okay. Because missing a real case is the ultimate failure here, the high recall approach of Model A is absolutely the right choice. We willingly accept the lower precision to ensure we save lives. Now, let's take those exact same AI characteristics and totally flip the scenario. You're building a spam filter for your email inbox. Model A is still high recall. It aggressively blocks all spam, but it catches some of your important emails in the crossfire. Model B is still high precision. It is very cautious, meaning it rarely blocks a good email, but a few pieces of spam might occasionally sneak into your inbox. In this situation, the math completely flips. A false positive here means wrongly blocking a genuinely important email, like an urgent message from your boss, or maybe a lucrative job offer. That is way more costly and infuriating than a false negative, which is just seeing one piece of junk mail in your inbox that you can delete in half a second. Because the false alarm is the bigger headache for us, your spam filter usually leans toward high precision, making Model B the clear winner here. It's the exact same metrics, but a completely opposite decision. Which brings us to Section 3, why this actually matters. Let's talk about the cost of mistakes. You know, the genuine core skill in machine learning isn't just memorizing complex math formulas or running Python code. It's really about understanding the real-world cost of a mistake for your specific problem. The golden rule is this: the choice depends entirely on what a false positive actually costs versus what a false negative actually costs. That single answer tells you whether you should be optimizing your model for precision, optimizing for recall, or trying to balance them right down the middle with the F1 score. You absolutely have to know the business problem before you can begin to judge the data problem. All right, Section 4, recap. Let's put this all together rapidly. Step 1, remember the accuracy trap. It will completely mislead you on rare event problems by just guessing the majority class every time. Step 2, if false alarms are your absolute biggest fear, precision is your best friend because it limits them. Step 3, if missing a real event is your biggest fear, lean heavy on recall because it ensures you catch those real cases. And finally, Step 4, when you need a model to just be reasonably competent at both without hiding its flaws, use the F1 score to balance them together. So I want to leave you with this final provocative thought. What does a mistake actually cost in your specific problem? Seriously, before you look at a single metric, answer that question. If you want to see this put into practice, comment the word classify below and I'll send you a real project walkthrough where we actually pick the right metric together. Don't forget to subscribe for more explainers that break down the complexity of AI, and I will see you all in the next one.